Bismillahirrahmanirrahim. Hello everyone. In this video tutorial I'm going to show you how to consider the vertical direction of an earthquake in the design of a structure. How the code provision recommend to consider. So in this topic we will quickly model a small 5 stories concrete structures and then applying specific ground motion and the vertical ground motion also considered in the response spectrum analysis and also in the time history analysis. So we use a metric and using this provision code. So okay, and next I'm going to select one of the predefined templates structure with flat slabs. Let's see the direction in number of grid line in the x direction should be 4 and y direction also be 4. In the spacing in the x direction will be 5 meters, in the y direction be 4.8 meters. So the number of stories 5 stories. First typical story is 3 point and first story is 4 meters. So we're going to flat slab. We can change the flat slab some left edge distance, and also we can accept these parameters, and also drop panels should be in a 3 meters panel zone as a square, and also we can add some dead load, pre-dead load. If we allow post tensioning, also we can check this, otherwise we can use without post tensioning. So this is 1.1 kilonewtons and kilonewtons per square meters dead load, and 4 kilonewtons per square meters live load. So the floor have a rigid diaphragm, and the slab thickness is 200 millimeters, and the column size is 3. I'm going to increase this about be 400, and the slab thickness can be 200 is enough. So we can say okay. Now we can have a typical structure with flat slabs. So here is we can show a rendering. We can see, so this is our structure. So it's a flat slab structure with just columns, and we don't have any sort of shear resisting system. So we are quickly going to define a shear wall. Go to the define and go to the section. Here is wall section. We can edit this shear wall. Let's see, we have a shear wall as a core area about 30 centimeters, 30 centimeters. And the concrete is 4000 psi, and it's a shell 10 elements, and here we should give 300. We're not going to reduce or change any other stiffener, so that's okay. Okay, we can go to quickly draw a shear wall in the center, and in the center of this, but we can draw as in as elevation, or also draw in a planar section. So here is let's see which is in all stories. I'm going to go to the draw, also it's wall opening, and wall opening, and now when you comes to the click in the this page, you need to activate it. So it's wall, and also we can quick draw wall, also draw our manually wall. So I'm going to use this method. So here is one uh, from here to here, one, and one wall from here to here, and the next is going to be other type of wall, but we can accept these three walls, and one so we're not going to add any sort of beams, so this is enough. Now we can see the wall location in as a 3D shape. Here is okay. Next we're going to define some load patterns. Load pattern, we want to apply a first static earthquake load, which is in a x direction. We can select seismic loads. From here we select ASC 716 add, and we can go to one more y, and now we can modify these lateral loads. So the parameter, which is very important, the first we should select x direction with 5% eccentricity. So the short period is 1.13, and 1 second is 0.6. So the long period transmission is about 8 seconds, and the soil is D, which is a stiff soil. Though it automatically calculate the FA, FEV, and also the design spectrums will be like this. So this is response spectrum, and this is our ground motion parameters, which we got from the map. So this is a ordinary composite, which is beam shear wall system, which required about 7, and the over strength is also 2.5, and this is 5. This is the occupancy is 1. So how we need to get from this the first one, calculate the period of the structure with these parameters, then OK, and the same we will apply for the y direction with the 5%. So we're going to use 1.13, and here is bound 6. It should be 0.6. So this is D, and here is 7, here is 2.5, and it's 5. It's okay. Now we defined EX, EY, and it's okay. And next is going to define modal cases. But before this, we want to consider we should have two actually. For response, we consider the vertical effects of the earthquakes in the response spectrum, and also for the time history. For this case, we should define at least two mass source. One is called this mass source 1. We want the load should be specified from 1 from date load, and 0.50 from the live load. For dynamic analysis, which is response spectrum analysis, a modal analysis is required. So we want the mass should include in a vertical. Um, okay, and this is okay. Um, the next is we are going to for the response curve, response spectrum, and we can use the ASC17 add a new function that we got called RS1. So we can give the same parameters here, 1, 3, and here is 0.60. So we select, yeah, in BD. Now this is the design curve. So the design curve, the maximum, which is here 0.7, and the in 1 second is here is B 0.68. So these are parameters in x direction with a 5% damping coefficient. Okay. This is a response spectrum. We define the same with equilateral methods. Okay, and the next is go to the load cases. We should check our load case. The load case, which is 5 stories, we can get at least. Here, 10 number of models enough for 10-story concrete structure, and other parameter can be a minimum is 1, and the convergence tolerance should be a very small number. We have two type of model. One is Ritz factor and also eigenvector. So we can select, but most of the time we recommend to use Ritz factor. So I can get Ritz factor. Here is we can select that mode should calculate in mode deformation should be in which direction. So we can calculate in x, y, z. Sorry, here should be select acceleration and needs to be z, y, and also one more. You should calculate in a z direction as well. So sometimes if you don't want to include vertical loads in the dynamic analysis, so you don't need to use z, but x, y is enough. But if you want to consider vertical earthquakes in your vertical earthquakes impacts or effects in the design or load combination, then you have to check this give one. So the maximum cycle we can give this 0 as default, and the target mass participation should be 99%. We can reduce, but it should be over 85%. So this is okay, and we defined a model. Now we're going to define a response spectrum analysis. We can say RS in x direction, which should consider with plus 30% of z. So we can just say like this and select your response, and here is acceleration in x direction should 100%. So this is the scale factor, which is 1J. So we are going to times, here is a scale factor method. You should use this one, I times J. The I is the important factor, and J is gravity load, and this is the R, which is reduction factor 7 we already got. Now this is actually J. We're going to times 1 and divided by 7. So this is the total 100% response spectrum curve, and we are going to select add one more, and this time we're going to select U3. We can make a copy of this, then paste divided by 3, so which is almost 30%. Now we consider the response spectrum in a z direction as well. So the load case should be modal, and the modal combination quadratic combination, and the directional of combination should be hysteresis. So we have a modal damping of 5%. This is okay. The next is going to the same response curve, but just in one RS X. So that means we're not going to include the z direction, but we can see that the differences with the z direction. So just in case of the effects of the z direction, we want to do this. So this is the same we got from copied from the previous, and there's no x, no z. So this is okay just for our work. That's okay. We want to see the response when we include the vertical acceleration and when we don't. So now we are going to save our model. 7 is called RS. We can call the vertical ground motion. So save, and we're going to quickly set load to run, and we want to turn on this diaphragm and run it. Actually, in some area, maybe the vertical earthquake effect is very high. I have seen in some recorded earthquake there is even similar the vertical direction recorded with horizontal and XYZ. So be sure if the region is very in a seismicity region, you should consider these parameters or this direction. Now we can check. The result is almost completed. We can check, and one thing is here, which if the response spectrum is less than 85%, then we should increase this by this factor. So I have already modeled to other examples tutorial. You can check, but in this particular example, just we will see the response of this vertical ground motion. Okay, I'm going to see in one case. So I'm going to select RS, which is 30%, included 30% of Z. I'm going to draw a curve to see the response and apply. This is it. This is it, which is a maximum. A maximum in the top is 2.5 millimeters. We can also go to the display. Here is called to response, and we can get the results here. So this is the first, which is a maximum, 2.6 millimeters. So the structure is very steep. We used a very large we use very large shear wall, so the structure is very strong and very stiff, so the deflection is quite small. And we can, when it's 2.36 millimeters, and we can check it with, so it's a little difference. So it's 2.3 and previous is 2.3. So in this case, sometimes we can ignore the vertical ground motions. Next is we can compare if our work is correct or not. I'm going to select the shear stories. So here is the maximum is the minimum, which is got in negative 1294 kilonewtons, and I'm going to see the response spectrum is 1600, so quite larger, which is not less than 85% of the equivalent lateral force, so it's greater, so that's almost can satisfy our code provision. In case if it's a less, then we will increase the scale factor. It should be over or equal. So this was the how we can consider. When we go to the load combination, we already defined in x, y, z direction. We can add load combination, and that time we can select this one instead of using RAX. And also one more thing is I'm going to check this was a RAX, and let's see what is the difference in. But in difference is the shear force is quite less, which is quite similar with equivalent lateral force. This is 1244, and this is 1290. So this was the results, and this is a almost advanced topic. Most of the time for simple structure we don't include vertical earthquake effects, so but for most of other structure we should include it. So here were the two parameters, shear force and displacement difference. So I hope this can solve your problem, and if there is any question you can put in the comment and I will find time to answer it. Thank you. See you for next time.